There's a question that lives in the space between wonder and mathematics. It emerges late at night when you're staring at stars that died millions of years ago. It appears in the quiet moments when you consider what time really means. Does time stop when you reach the speed of light? The question feels simple, almost childlike in its directness, but contained within these 8 words is a universe of mystery, a puzzle that touches the deepest nature of reality itself. We've all heard something about Einstein, about relativity, about light being special somehow. We've absorbed fragments of ideas from documentaries and science fiction. Time slows down when you go fast. Nothing can travel faster than light. These phrases float in our collective consciousness like distant signals from a world we don't quite understand. But tonight, we're going to understand. Not in the way a physicist understands, with equations dancing across blackboards, but in the way a human being understands, with intuition, with careful thought, with the kind of clarity that comes when you strip away the complexity and look directly at what's real. Because here's what most people don't realize. The question itself contains a hidden assumption, a subtle trap built into its very structure. When we ask if time stops at light speed, we're already making a mistake. We're asking the wrong question in the wrong way, and that's where we need to begin what we think we know. Let me take you back to childhood. Remember learning about speed? Your teacher might have drawn a car on the board, shown you how distance divided by time gives you velocity. If you drive 60 miles in 1 hour, you're going 60 miles per hour. Simple, elegant, obvious. Then maybe they told you about the speed of light, about how light travels at 186,282 miles per second, about how nothing in the universe can go faster. And maybe you thought, okay, that's just a really big speed. The ultimate speed limit, like the fastest car anyone could ever build. But light speed isn't just a big number. It's something else entirely. It's not the universe's way of saying, this is as fast as you can. Go. It's the universe's way of revealing something profound about the structure of reality itself. When Einstein published his special theory of relativity in 1905, he wasn't trying to set a cosmic speed limit. He was trying to solve a puzzle. A beautiful, maddening puzzle about how light behaves. The puzzle was this. Light always moves at the same speed. Always. No matter who measures it. No matter how fast they're moving when they measure it. If you're standing still and you measure the speed of light, you get 182 miles per second. If you're in a spaceship moving at half the speed of light and you measure the speed of light, you get the same number, 186,282 miles per second. This shouldn't be possible. Think about it this way. You're standing on the side of a highway. A car drives past you at 60 miles per hour. You measure its speed with a radar gun, 60 miles per hour. Now imagine you're in your own car, driving at 30 miles per hour in the same direction. When that first car passes you, what speed does your radar gun show? 30 miles per hour, right? Because relative to you, the other car is only going 30 miles per hour faster than you are. This is how the universe should work. This is how speeds should add and subtract. This is what common sense tells us. But light doesn't obey this rule. Light doesn't care how fast you're moving. It always recedes from you at exactly the same speed, as if it's always the same distance away, as if it exists in some strange relationship to space and time that nothing else shares. Einstein looked at this impossibility and realized something shocking. The universe wasn't broken. Our understanding was broken. We had been thinking about time wrong. We had been thinking about space wrong. We had been thinking about reality wrong. The architecture of space-time. To understand what happens at the speed of light, we need to rebuild our intuition from the ground up. We need to stop thinking about space and time as separate things. We need to start thinking about space-time. Imagine you're in a room. You can move forward and backward. You can move left and right. You can move up and down. These are the 3 dimensions of space. They're obvious, tangible. You can point in these directions with your finger. Now add time. Time is also a dimension. You're always moving through it. 1 second per second, always forward, never backward. Never standing still in the time dimension. But here's what's not obvious. Space and time aren't independent. They're woven together into a single fabric. A 4-dimensional fabric called space-time. When you move through space, you change your movement through time. When you speed up in the spatial dimensions, you slow down in the time dimension. They balance each other. They trade places in a precise mathematical dance. Think of it like this. You have a certain amount of motion available to you, a certain amount of movement through space-time. You can spend this motion moving through space, or you can spend it moving through time, but you can't spend it twice. When you're sitting perfectly still in a chair, not moving through space at all, you're moving through time at maximum speed. 1 second per second, time passes normally. Clocks tick at their regular pace. But when you start moving through space, something has to give. You can't move through space without stealing that motion from your movement through time. The faster you go through space, the slower you go through time. This isn't a metaphor. This isn't a thought experiment. This is how the universe actually works. When you drive your car, you're aging microscopically slower than someone standing on the sidewalk. When astronauts orbit Earth at 17,000 miles per hour, they age about 0.007 seconds less per 6 months than people on the ground. GPS satellites have to account for time dilation, or they'd give you directions that are wrong by miles. The effect is real, measurable, undeniable. And as you approach the speed of light, this effect becomes dramatic, not just noticeable. Dramatic in ways that shatter our everyday intuition. The twin paradox. Let me tell you a story. It's called the twin paradox, and it's one of the most famous thought experiments in physics. Imagine 2 twins. Let's call them Sarah and Maya. They're identical in every way. Same age, same birthday, born minutes apart. They celebrate their 20th birthday together, surrounded by family and cake and laughter. Then Sarah makes a decision. She's going to become an astronaut. She's going to travel to a distant star system. The journey will take her to speeds approaching the speed of light. Maya stays on Earth. She gets a job, falls in love, starts a family, lives an ordinary human life. Sarah's journey takes what seems to her like 5 years. 5 years of watching the stars stream past her window. 5 years of solitude and wonder. 5 years of moving through space at 95% of the speed of light. Then she turns around. 5 more years to come home. 10 years total from her perspective. When Sarah arrives back on Earth, she's 30 years old. She's aged 10 years since she left. But when she steps off her spacecraft, Maya is there waiting. Except Maya isn't 30, Maya is 70 years old. Maya has lived 50 years while Sarah lived 10. This isn't science fiction. This is Einstein's relativity. This is what the mathematics predicts. This is what would actually happen. Sarah's speed through space was so great that her movement through time became slow. Glacial. 1 year for her was 5 years for Maya. The twins' relationship to time itself became different. Fundamentally, physically, measurably different. And this is at 95% of the speed of light. Not even at the speed of light itself. Just close to it. So what happens when you actually reach light speed? What happens when you push that speedometer all the way to 186, 282 miles per second? This is where the question becomes strange. The photon's perspective. Let's try something impossible. Let's try to imagine what it's like to be a photon. A particle of light. You're born in the core of the sun, created in a fusion reaction where hydrogen atoms merge into helium. Energy is released. That energy becomes you, a photon. A quantum of light. You begin moving, not accelerating, just instantly moving at light speed. Because photons don't accelerate. They don't have a resting state. They exist only as motion itself. You bounce around inside the sun for thousands of years. The sun is dense, opaque. Each time you try to escape, you hit another particle. Get absorbed. Get re-emitted. The journey from the sun's core to its surface takes a photon about 100,000 years of random pinball collisions. But finally, you make it. You break free from the sun's surface. And now there's nothing in your way. 8 light minutes of empty space between you and Earth. From Earth's perspective, your journey takes 8 minutes. 8 minutes for you to cross 93 million miles. Humans on Earth look up at the sun, and they're seeing you 8 minutes in the past. 8 minutes ago you left. Now you arrive, but from your perspective, from the photon's perspective, no time passes at all. The moment you leave the sun is the same moment you hit a human's retina on Earth. There is no duration, no journey, no passage of time. You exist at your departure and arrival simultaneously. This is what time dilation looks like at the speed of light. Time doesn't just slow down, it stops. Completely. Utterly. Absolutely. From a photon's perspective, the universe is infinitely compressed along its direction of motion. The sun and Earth occupy the same point in space. The photon experiences no time, no space, no journey. It exists in an eternal now, a single frozen moment that spans 8 light minutes for everyone else, but no distance at all for the photon itself. This is the answer to our question. Does time stop when you hit the speed of light? Yes, completely. And this is the crucial but, the important but, the but that changes everything. You can't hit the speed of light. Why you can't touch light speed? This is where we need to talk about mass, about energy, about why the speed of light isn't just a speed limit, but an impossible boundary. Everything that has mass has inertia, resistance to acceleration. The more massive something is, the harder it is to push, to change its velocity, to make it go faster. Your car has mass. When you press the gas pedal, you're using the energy from burning gasoline to overcome the car's inertia, to accelerate it, to add velocity. The faster you're already going, the more energy you need to go faster still. This makes intuitive sense. Accelerating from 0 to 30 miles per hour is easier than accelerating from 70 to 100 miles per hour. But here's what doesn't make intuitive sense. As you approach the speed of light, the energy required to accelerate doesn't just increase. It increases without limit. It approaches infinity. To accelerate a single electron to the speed of light would require infinite energy. Not a lot of energy. Not more energy than exists in the observable universe. Literally infinite energy. This isn't a technological limitation. It's not that we haven't built a powerful enough engine yet. It's that the universe itself forbids this acceleration. The mathematics of relativity creates an asymptotic barrier. You can get closer and closer to light speed. 90%. 99%, 99.999999999%, the universe from a photon's view. But let's stay with the photon a little longer. Let's explore this impossible perspective, because even though we can't experience it ourselves, understanding it tells us something profound about the nature of time. Imagine you are a photon leaving a distant galaxy. This galaxy is 10 billion light years from Earth. From Earth's perspective, your journey will take 10 billion years. 10 billion years of crossing the empty void between galaxies. 10 billion years while Earth forms from dust, while life evolves, while humans emerge and build telescopes to see you coming. The structure of now. Let's pull back from the photon and return to our own perspective, because we need to understand something that's easy to miss. Time dilation isn't about clocks running slow or fast. It's about the fundamental structure of now. You exist in a now, this moment, this instant you're experiencing right now as you hear these words. You think of now as universal. You think everyone in the universe shares the same now, the same present moment. They don't. Right now, as you experience this moment, what's happening on a planet orbiting a star 10 light years away? What's the current moment there? The question has no answer. Not because we don't know, but because there is no single answer. The concept of right now on that distant planet is meaningless, undefined. That planet's now depends on your reference frame, on your velocity, on how you're moving. If you're sitting still, the planet's now might be May 15th, 2025. But if you're moving toward that planet at 90% of light speed, its now might be January 3rd, 2025. If you're moving away from it at 90% of light speed, its now might be September 30th, 2025. All three answers are equally valid. Equally true, there is no absolute now. No universal present moment that all observers share. This is called the relativity of simultaneity. It's one of the strangest implications of Einstein's theory. Events that are simultaneous in one reference frame are not simultaneous in another. The order of events can even change depending on how you're moving. What time actually is? We need to step back even further. We need to ask a more fundamental question. What is time? We experience time. We feel it passing. We remember the past. We anticipate the future. We exist in an ever-moving present that seems to flow from yesterday into tomorrow like a river carrying us along. But what is this thing we're experiencing? What is the nature of this temporal flow? Physics has an answer that might surprise you, an answer that might disturb you. Time, in physics, is just another dimension, similar to space, a direction you can point in, a coordinate you can specify, the when of an event, like the where of an event. When we write down the equations of physics, time appears as a variable, a number, a coordinate in a four-dimensional space-time. It plays a role similar to the spatial dimensions, with some mathematical differences, but fundamentally the same kind of thing. But this raises a problem. The physics equations don't care about past and future. They work the same whether time runs forward or backward. If you film a planet orbiting a star and play the film in reverse, the motion still obeys Newton's laws, still follows the equations perfectly. The fundamental laws of physics are time-symmetric. They don't distinguish between past and future. They don't include an arrow of time, and yet we experience an arrow of time. Very clearly, undeniably, eggs break but don't unbreak. We age but don't unage. We remember the past but not the future. Where does this arrow come from? If the fundamental laws are time-symmetric, why does time seem to flow in only one direction? The answer is entropy. The second law of thermodynamics, the tendency of disorder to increase. Imagine a drop of ink falling into a glass of water. The ink spreads out, diffuses, distributes itself evenly throughout the water until the entire glass is a uniform light blue. This process only goes one direction. The ink doesn't spontaneously gather itself back into a drop. Order decreases, entropy increases. This is the arrow of time. But here's the deep question. Is entropy fundamental? Is the increase of disorder a real feature of time itself? Or is it just a statistical pattern, a consequence of how likely different arrangements are? If you could see every molecule in the glass of water, you'd see them bouncing around randomly, following Newton's laws perfectly, each collision reversible, each interaction time-symmetric. The ink spreads not because of some fundamental law about disorder, but because there are so many more ways for the ink molecules to be spread out than concentrated. It's probability, statistics. The universe exploring all possible arrangements and spending more time in the arrangements that are more numerous. This suggests something strange. Time's arrow might be an illusion, a statistical phenomenon that emerges from our macroscopic perspective, from our inability to track every molecule individually. At the fundamental level, at the level of individual particles following individual laws, there might be no arrow at all. No real distinction between past and future. Just a four-dimensional space-time where all moments exist equally, where time doesn't flow but simply is. The block universe. This brings us to a radical idea, an idea that many physicists take seriously. The block universe. Imagine the entire history of the universe laid out in four-dimensional space-time. Every moment that has ever existed, every moment that will ever exist. All of it together in one eternal structure. Your birth is in there, a point in space-time. Your death is in there too, another point in space-time. Every moment of your life exists as a slice through this four-dimensional block, a continuous path through space-time called your world line. In this view, past, present, and future all exist equally. The past hasn't ceased to exist. The future hasn't failed to exist yet. They're all just different regions of space-time, different locations in the four-dimensional universe. The present moment you're experiencing right now, it's just your current location in space-time, as real as your current location in space. No more privileged, no more special. Time doesn't flow in the block universe. It doesn't pass. You don't move through time. You exist at all moments of your life simultaneously. Your consciousness experiences these moments sequentially because of how memory works, because of the thermodynamic arrow, because of entropy. But the moments themselves don't flow. They just are. Eternally, timelessly, all of them together in the unchanging structure of space-time. This is called eternalism, the view that all times are equally real, that the universe is a four-dimensional block where past, present, and future coexist. If eternalism is true, then time is very different from how we experience it. There is no objective passage of time, no universal now, no moment that is uniquely the present. And at the speed of light, where time dilation becomes infinite, this becomes even clearer. The photon experiencing all moments of its existence simultaneously isn't doing something special. It's just experiencing reality as it actually is, without the illusion of temporal flow, without the experience of moving from past to future. We, with our massive bodies and slow speeds, experience time as flowing. We feel ourselves moving through it. But this might be a limitation of our perspective, an artifact of our reference frame. The universe itself might be timeless, eternal, all moments existing together in an unchanging four-dimensional whole. The speed of light is a cosmic translation. Let's think about the speed of light in a new way, not as a speed limit, not as the fastest you can go, but as a conversion factor, a translation between space and time. You know how you can convert miles to kilometers? There's a conversion factor, 0.69 kilometers per mile. It's not that kilometers are faster than miles or better than miles. They're just different units measuring the same thing. The speed of light is similar. It's the conversion factor between time and space. It tells you how much space equals how much time, how to translate a distance into a duration. Light travels 186,282 miles per second. Another way to say this, 1 second equals 186,282 miles. These are equivalent statements. 1 second of time is the same as 186,282 miles of space. They're interchangeable in the mathematics of space-time. This is why light speed is the same for all observers. It's not actually a speed. It's the structure of space-time itself. It's the ratio that defines how space and time relate to each other. When you try to accelerate to the speed of light, you're not trying to go really fast. You're trying to transform completely from a time-like trajectory to a light-like trajectory. You're trying to change what kind of thing you are. Objects with mass have time-like world lines. They move primarily through time. Their path through space-time is mostly in the time direction. Light has light-like world lines, null world lines that are exactly balanced between space and time. They form the boundary between what's possible to reach and what's not. Imagine space-time as a piece of paper. Time is vertical, space is horizontal. Your world line, your path through space-time, draws a line on this paper. If you're standing still, your line is purely vertical, straight up the page, moving through time, not through space. If you're moving, your line tilts. Part of your motion is through space now. The faster you move, the more your line tilts. But there's a limit to how much it can tilt. A maximum angle, the angle of a light ray. You can approach this angle, but never reach it. Your world line can tilt further and further, but it can never become horizontal, can never be purely spatial. Light rays sit exactly at this boundary angle. Not vertical, not horizontal, exactly at the boundary between them. This is what makes them special. The speed of light is the speed of causality, the speed of cause and effect, the speed at which influences propagate through space-time. It's not about light specifically. Light just happens to travel at this speed because photons have no mass. If we discovered tomorrow that photons actually have a tiny bit of mass, they would travel slightly slower than the speed of light. But the speed of light would still be the same. It's not about the photons, it's about the structure of space-time itself. Tachyons and impossible particles. Let's play with an impossible idea. What if something could go faster than light? Physicists have imagined such particles. They call them tachyons. Hypothetical particles that always travel faster than light speed. Not particles that accelerate past light speed. That's impossible. But particles that exist only on the other side of the light barrier. If tachyons existed, they would be strange. Stranger than anything in our everyday experience. For one thing, they would have imaginary mass, not zero mass like photons. Imaginary mass, a mass value that involves the square root of -1. They would also violate causality. From some reference frames, a tachyon would arrive before it was emitted. You could use tachyons to send signals into your own past, to create causal loops, grandfather paradoxes. If you could send a signal faster than light, you could send it to someone moving at a different velocity, and from their perspective, the signal arrives before you sent it. They could send a response back, and from your perspective, their response arrives before you sent your original signal. This creates a paradox. You receive a response before you sent the question. You could use this response to decide not to send the question. But if you don't send the question, how did you receive the response? The universe seems to forbid this, not as an arbitrary rule, but as a consequence of how space-time is structured. Faster than light travel and causality can't both be true. One must give way. The universe chooses causality. Cause must come before effect. Information can't travel faster than light. The speed of light is the speed of cause and effect itself. Some physicists have speculated that if tachyons exist, they might be undetectable, unable to interact with normal matter, forever trapped on the other side of the light barrier, unable to influence our world. Others argue that tachyons are simply impossible, mathematical artifacts with no physical meaning, curiosities in the equations, but not residents of reality. Either way, no tachyon has ever been detected. No evidence suggests they exist. The speed of light remains an absolute barrier, an unbreakable limit on causality and information, the experience of time. Let's return to something more personal, more immediate, the experience of time itself. You've felt time move at different speeds. Everyone has. A boring afternoon drags on forever. An exciting evening vanishes in what feels like minutes. We talk about time flying, about time crawling, about losing track of time. But the clock always ticks at the same rate. Seconds pass steadily, relentlessly, 1 per second. So what's changing? Not time itself, your perception, your experience, your psychological relationship with duration. When you're bored, you're paying attention to time, checking the clock, counting minutes, waiting for something to happen. This makes time feel slow. Each moment stretched out by your attention. When you're engaged, absorbed, enjoying yourself, you're not paying attention to time. You're focused on what you're doing. Lost in the flow of activity, time passes unnoticed. Hours disappear. This is entirely psychological. But it's real as any physical phenomenon. Your experience of time is not the same as physical time. They're related but distinct. Children experience time differently than adults. For a child, a year is a huge fraction of their entire life. A year is forever. Seasons take ages to change. Summer vacation is an eternity. For an adult, years slip by with increasing speed. A year becomes a smaller and smaller fraction of total life experience. Decades pass in what feels like moments. Some psychologists think this is about novelty. Children experience everything as new. Every day brings unfamiliar experiences, new things to learn, new patterns to recognize. This richness of experience makes time feel long. Adults settle into routines. The same commute every day, the same work, the same evening rituals. Days blur together. Weeks become indistinguishable. Time accelerates because nothing notable happens to mark its passage. If you want to slow down your experience of time, seek novelty. Travel to new places. Learn new skills, break your routines, create memorable experiences. These experiences become markers in your memory. They stretch out your perceived duration of life. But this is all psychology, all neuroscience, all about how the brain processes and remembers experiences. Physical time, objective time, the time measured by clocks and defined by relativity, is different. It doesn't care about your attention or your novelty or your engagement. And yet, the two are connected, because you don't experience physical time directly. You only experience your brain's representation of time. Your consciousness exists in the psychological time domain, while your body exists in the physical time domain. At extremely high speeds, these two domains intersect in strange ways. Time dilation isn't psychological, it's physical, measurable, real. But from the inside, from the perspective of the person experiencing it, time still feels normal. 1 second per second. The flow of consciousness unchanged. Sarah, the twin who traveled at relativistic speeds, didn't feel time moving slowly. From her perspective, time moved normally. It was only when she returned to Earth and saw Maya aged 50 years that she realized something had happened, that her time and Earth's time had diverged. The quantum connection. We need to talk about quantum mechanics, because when you combine relativity with quantum theory, something beautiful and strange emerges. In quantum mechanics, particles don't have definite positions or velocities until you measure them. They exist in superpositions, in multiple states at once, smeared out across space in a probability cloud. The famous double-slit experiment demonstrates this. Fire a single electron at 2 slits. Don't measure which slit it goes through. The electron interferes with itself, creates an interference pattern on the screen behind the slits, as if it went through both slits simultaneously. But measure which slit the electron goes through, and the interference pattern disappears. The electron goes through one slit or the other, not both. The act of measurement collapses the superposition, forces the electron to choose, to become definite. Now add relativity. Add the fact that simultaneity is relative, that different observers disagree about when events happen. When does the measurement happen? When does the superposition collapse? If two observers are moving at different velocities, they'll disagree about the timing. One observer might see the measurement happen before some other event. Another observer might see it happen after. This creates a puzzle. If the measurement collapses the superposition, and different observers disagree about when the measurement happens, do they also disagree about when the collapse happens? This is called the measurement problem in quantum mechanics, made worse by relativity. It's unresolved. Different interpretations of quantum mechanics handle it differently. Some interpretations say the collapse is real, physical, happening at a definite moment. These interpretations struggle with relativity. They need to identify a preferred reference frame, a universal now, but relativity says there is no such thing. Other interpretations say collapse isn't real. The superposition never collapses. All possibilities continue to exist in parallel. The universe branches into multiple worlds, many worlds, each world experiencing a different outcome. In the many worlds interpretation, there's no collapse problem. No need for a preferred reference frame. All possibilities are real. Relativity is satisfied because nothing discontinuous happens. No moment of collapse to argue about. But this creates its own mysteries. Where are these other worlds? How do they relate to each other? Why do we experience only one outcome? The point is this. When you combine relativity with quantum mechanics, strange things happen. Time becomes even more mysterious. The nature of events becomes uncertain. The universe reveals layers of complexity that challenge every intuition. And at the speed of light, where time stops, quantum effects become even more important. Particles at light speed live in both the quantum realm and the relativistic realm. They experience the full strangeness of both theories simultaneously. Why light speed matters for life. Let's think about why the speed of light has the value it does. Why 186,282 miles per second? Why not faster? Why not slower? This is a deep question, one that touches on something called the anthropic principle, the idea that the universe must be compatible with the existence of observers. Because if it weren't, we wouldn't be here to observe it. The speed of light determines many things about how the universe works. It sets the scale of causality. It determines how far influences can propagate in a given time. It affects how stars form, how planets evolve, how life emerges. If light speed were much faster, the universe would be very different, more tightly connected. Cause and effect would span larger distances, but also stars would burn differently. Nuclear fusion would proceed at different rates. The chemistry of life might not work. If light speed were much slower, the universe would be fragmented, isolated. Regions of space would be causally disconnected for longer times. Galaxies might not form properly. The cosmic web of structure might not emerge. The actual value of light speed, along with other fundamental constants, seems finely tuned, balanced in a way that allows complex structures to form, stars to shine, planets to cool, life to emerge and evolve. Some physicists take this as evidence of multiple universes, a multiverse where different regions have different values of the fundamental constants. We find ourselves in a region where the constants allow life, because that's the only kind of region where observers can exist. Others see it as evidence of design, of intention, of purpose behind the physical laws. Still others say it's just coincidence, or that we don't yet understand the deeper principles that fix these constants. That someday we'll discover a theory that predicts their values. That explains why light speed must be what it is. But regardless of why light speed has its particular value, the fact remains that it's central to existence, to how matter interacts, to how information flows, to how time and space weave together into the fabric of reality. Without light speed being what it is, you wouldn't be here. The atoms in your body wouldn't have formed. The stars wouldn't have created the heavy elements. The earth wouldn't have cooled at the right rate. Evolution wouldn't have had time to unfold. Light speed is written into the deepest structure of existence. It's not just a number in a physics textbook. It's part of the architecture of being itself. The singularity at light speed. Let's return to our original question with fresh eyes. Does time stop when you hit the speed of light? We now understand that the question contains an impossibility. You can't hit the speed of light. Nothing with mass can. The mathematics forbid it. Energy requirements become infinite. Mass itself appears to increase without limit as you approach light speed. But mathematically, we can ask what happens at the limit. What happens as velocity approaches light speed? What does time dilation approach? The answer is clear. Time dilation approaches infinity. From the perspective of a stationary observer, time on the moving object slows down more and more, approaching zero, approaching a complete stop. At exactly light speed, time dilation is infinite. Time stops, completely, absolutely. No time passes whatsoever. This is a singularity in the equations, a point where the mathematics breaks down, where infinite values appear, where the predictions become undefined. Singularities appear elsewhere in physics, at the center of black holes. At the moment of the Big Bang, they mark the boundaries of our theories, places where our current understanding fails, where new physics is needed. The singularity at light speed tells us something important. It tells us that massive objects and massless objects live in fundamentally different realities. They experience space-time in incompatible ways. For massive objects, time is real. Motion is possible. Change happens. Clocks tick. Processes unfold. The universe evolves from moment to moment. For massless objects traveling at light speed, none of this exists. No time, no duration, no process, no change. Just eternal, timeless existence at all points along their path simultaneously. These are not two different perspectives on the same reality. They are genuinely different modes of existence, different ways of relating to space-time itself. You cannot smoothly transition from one to the other. There is no continuous path from massive existence to massless existence. The transformation would require infinite energy, would require passing through the singularity. This is why the question breaks, why it has no answer. You're asking what it's like to transition between incompatible modes of existence, between fundamentally different ways of being. Light is pure geometry. Here's another way to think about light, as pure geometry, as the structure of space-time made visible. In Einstein's general relativity, gravity isn't a force. It's the curvature of space-time. Mass tells space-time how to curve. Space-time tells mass how to move. This is Wheeler's famous summary. Matter tells space-time how to curve, and space-time tells matter how to move. Light follows geodesics, the straightest possible paths through curved space-time. A geodesic is what you get when you try to travel in a straight line through a curved space. On a flat surface, a straight line is obvious. It's the shortest distance between 2 points. But on a curved surface, like the surface of a sphere, straight lines become curves. The straightest path between 2 points on Earth's surface is a great circle, the path airplanes follow when they fly long distances. Light does this in 4-dimensional space-time. It follows the geodesics, the straightest paths, the null geodesics to be precise, paths where the space-time interval is exactly 0. This means light rays are pure geometry. They're not objects moving through space-time. They're features of space-time itself, threads woven into the fabric, lines that define the structure. When you see a star, you're seeing along a geodesic, a path through space-time connecting the star's past to your present. The light didn't travel along this path. The light is this path, made manifest, turned into energy, into photons that your eye detects. This geometric view explains why light speed is absolute, why it's the same for all observers. It's not a speed in the traditional sense. It's the structure of space-time, the shape of reality, the geometry that underlies all motion and change. Objects with mass move through this geometry. They follow time like geodesics, paths that have non-zero space-time intervals, paths that include a temporal component, a flow through time. Objects without mass follow null geodesics, paths with 0 space-time interval, paths that balance space and time perfectly, that exist at the boundary between motion and stillness. Neither type of object is more fundamental. Both are expressions of space-time geometry. Both follow the straightest paths through the 4-dimensional manifold. But they follow different types of paths, incompatible types, types that cannot transform into each other. The information horizon. The speed of light creates horizons, not just at black holes, everywhere, in every direction. Horizons of causality, regions of space-time that cannot influence each other. Imagine you're standing on Earth. There are distant galaxies, galaxies so far away that light from them hasn't had time to reach us since the Big Bang. These galaxies are beyond our horizon. We can never see them, never receive information from them, never be causally connected to them in any way. As the universe expands, this horizon changes. Some galaxies that were once visible drift beyond our horizon. Their light, though already on its way to us, gets stretched by expansion, redshifted, eventually redshifted so much that it becomes undetectable. Other regions of space are accelerating away from us faster than light. Not moving through space faster than light, which is impossible, but space itself expanding between us and them faster than light can cross it. These regions are forever beyond reach, forever unknown, forever separate from our causal domain. The speed of light defines these horizons. It determines what can influence what can know about what can interact with what. In a very real sense, the observable universe is the only universe. Everything beyond our horizon might as well not exist. It can never affect us. We can never affect it. No information exchange is possible. No causal relationship exists. This is why faster-than-light travel appears so often in science fiction. It's not just about going fast. It's about connecting causally separated regions, about breaking through the horizons, about making the unreachable reachable. But the universe seems committed to these horizons, to maintaining causal boundaries, to preventing paradoxes, and preserving the logical structure of cause and effect. The speed of light is the speed of causality, the speed at which the future influences the past, the speed at which effects propagate from causes, and this speed cannot be exceeded. At light speed itself, time stops. The photon experiences no duration between emission and absorption. It exists at both ends of its journey simultaneously. It is the connection between cause and effect made physical, made real. The dark side of relativity. There's something unsettling about relativity, something that bothers people when they first encounter it. The loss of absolute time, the loss of a universal now. We're used to thinking of time as a river, flowing from past to future, carrying everything with it. We imagine the present moment as a universal slice through this river, a moment that everyone shares, where everything happens at once. Relativity destroys this picture. There is no universal moment, no absolute simultaneity, no shared now. Your now is different from my now if we're moving at different velocities, and both our nows are equally valid, equally real. This feels wrong. It feels like it should create contradictions. If your present is my past, and my present is your future, doesn't that break causality? Doesn't that allow time travel paradoxes? It doesn't. And understanding why reveals something deep about how space-time protects itself, about how the universe maintains logical consistency. The key is the light cone. At every point in space-time, you can draw a light cone, a boundary that divides space-time into 3 regions. The past light cone contains all events that could have influenced this point, all events that could have sent light signals that reached this point. The future light cone contains all events that this point could influence, all events that light signals from this point could reach. Outside both cones is the elsewhere, events that are too far away to have any causal connection, events that cannot influence this point and cannot be influenced by this point. Events in the elsewhere have ambiguous time ordering. Different observers disagree about whether they happened before or after the point in question. But this doesn't matter, because they're causally disconnected. They can't influence each other anyway. Events inside the light cones have definite time ordering. All observers agree about whether they happened before or after. Causality is preserved, because always comes before effect. From every perspective, this is how the universe maintains consistency, by making simultaneity relative only for causally disconnected events, by keeping causal ordering absolute, by ensuring that disagreements about timing never create logical problems. The speed of light enforces this structure. It defines the boundaries of the light cones. It determines what can influence what. It protects causality while allowing time itself to be relative. Acceleration and equivalence. We've been talking about constant velocities, about moving at steady speeds. But what about acceleration? What about changing velocity? This is where Einstein's general theory of relativity comes in, the extension of special relativity that includes gravity and acceleration. Einstein's key insight was the equivalence principle, the idea that acceleration and gravity are the same thing, indistinguishable. A person in an accelerating rocket feels exactly the same as a person standing on the surface of a planet. Both feel a force, both feel weight, both feel pressed against the floor. You can't tell the difference between gravity and acceleration from inside a closed room. They're equivalent, 2 descriptions of the same phenomenon. This equivalence has profound implications. It means gravity isn't a force pulling on objects. It's the geometry of space-time. Mass curves space-time, and objects follow the straightest paths through this curved geometry. What we perceive as gravitational attraction is actually objects following geodesics in curved space-time. Near a massive object, space-time is curved. Time runs slower, distances are distorted. This is gravitational time dilation. Time passes more slowly at the bottom of a gravity well than at the top. GPS satellites orbit Earth at high altitude. They're farther from Earth's center, farther from the bulk of Earth's mass. Time runs slightly faster for them than for people on the ground. But the satellites are also moving at high speed, about 8,600 miles per hour. This causes time dilation from special relativity. Time runs slower for moving objects. Both effects are real. Both must be accounted for. The GPS system needs to correct for both gravitational time dilation and velocity time dilation. If it didn't, positions would be wrong by miles within hours. Acceleration creates similar effects. If you're in a rocket accelerating at 1g at constant acceleration, time will dilate. Clocks at the front of the rocket will run faster than clocks at the back. Light will be redshifted traveling from back to front. This is called the twin paradox resolution. Sarah, traveling to the distant star, had to accelerate, had to turn around, had to decelerate. These accelerations broke the symmetry, made her reference frame different from Maya's, made her the twin who aged less. It's not just velocity that causes time dilation, it's also acceleration and gravity. All are aspects of the same underlying phenomenon. The curvature of space-time, the geometry of reality itself. And at light speed, these effects become infinite, singular, undefined. Light follows null geodesics, zero space-time interval, zero proper time, existing outside the normal rules of massive objects. The universe's speed limit. People often ask why. Why does the universe have a speed limit? Why can't we go faster? What would break if we could? The answer is about consistency, about logic, about causality, about the structure of reality being coherent rather than contradictory. Imagine a universe without a speed limit, where information could travel infinitely fast, where you could affect things instantly at any distance. In such a universe, there would be no time, not in any meaningful sense, because if effects propagate instantly, then cause and effect are simultaneous everywhere. The entire universe would be locked into a single moment. No change would be possible. No process could unfold. No time could pass. Time requires delay, requires a gap between cause and effect, requires processes to take duration to complete. The speed of light provides this delay. It separates causes from effects. It allows processes to unfold. It creates the space for time to exist. But why this particular speed? Why 186,282 miles per second? This is where we encounter the deep mystery. The fundamental constants of nature seem arbitrary. They have the values they have. We can measure them, use them in equations, make predictions, but we don't know why they have these particular values. Maybe there's a deeper theory, a theory of everything that predicts all the constants. That explains why light speed must be what it is, why the fine structure constant has its value, why the mass of the electron is what it is. Or maybe there's a multiverse, infinite universes with different constants. We exist in this one because it's compatible with our existence. The anthropic explanation, or maybe it's just brute fact. The universe is this way. The constants have these values. No deeper explanation exists or is possible, we don't know. This is the frontier of physics, the edge of understanding, the place where science meets mystery. But what we do know is this. The speed of light is fundamental. It's woven into the structure of space-time. It's not just a property of light. It's a property of reality itself, of causality, of the relationship between space and time. And at this speed, time stops. Not because physics breaks down, though the equations do produce infinities, but because at this speed, you're no longer moving through space-time in the way massive objects do. You're existing as pure connection, pure relationship, pure geometry, the philosophical implications. Let's step back from the physics. Let's think about what this means, what it implies about the nature of existence. If time is relative, if there's no universal now, if the past and future exist as real as the present, then what does this mean for free will, for consciousness, for identity? You think of yourself as existing in the present moment, as moving through time, as having a past that's gone and a future that's not yet real. Your decisions feel free, your choices feel open, the future feels uncertain. But if the block universe is real, if all moments exist equally, then your entire life already exists. Past, present, and future, all of it laid out in space-time. Your future decisions are already there, already part of the eternal structure. Does this mean free will is an illusion? That your choices are predetermined? That everything is fixed and unchangeable? Not necessarily. The block universe doesn't say your choices aren't free. It says all your free choices exist together in space-time. Your decision tomorrow exists in the same way your decision yesterday exists. Both are real. Both are part of the structure. But the decision tomorrow is still your decision. Still free. Still chosen. The question of whether free will exists is separate from the question of whether the future exists. You can have both. The future can be real, and your choices can still be free. Freedom doesn't require the future to be non-existent. It requires your choices to be truly yours. Not forced, not determined by external factors beyond your control. This is called compatibilism, the view that free will and determinism are compatible, that you can have both. That the existence of the future doesn't negate the reality of choice, but some philosophers disagree. They say if the future exists, then it's fixed. And if it's fixed, you can't change it. Your choices are illusory. You're just playing out a script that's already written. This debate isn't resolved. It touches on deep questions about consciousness, identity, and what it means to be a person. Questions that physics alone can't answer. But relativity does force us to confront these questions, to think carefully about time, about what exists, about what it means for something to be real. And at the speed of light, these questions become even more acute. Because at light speed, all moments collapse into one. Past and future are simultaneous. There is no duration, no process, no unfolding, just eternal existence. What would it mean to have consciousness at light speed? Could a photon be aware? Could it experience anything? Probably not. Consciousness seems to require time, require processes, require changes in neural states, require information processing over duration. Without time, consciousness seems impossible. Awareness requires before and after, requires memory forming from present experience, requires anticipation of future possibilities. A photon has none of this, exists in timeless stasis, experiences nothing, is nothing more than geometric connection made physical. Or maybe we're wrong. Maybe consciousness is more fundamental than we think. Maybe awareness exists at levels we don't understand. Maybe even a photon has some primitive form of experience. We don't know. Consciousness is still a mystery. Perhaps the deepest mystery, the hard problem. The question of how subjective experience arises from objective physical processes, time travel paradoxes. If we're talking about time and relativity, we need to address time travel, the possibility of visiting the past, of changing history, of creating paradoxes. Special relativity by itself doesn't allow time travel. You can't go backward in time. Time dilation lets you travel into the future by aging slowly while the universe ages quickly. But there's no mechanism for going backward. General relativity is more permissive. When you include gravity and curved space-time, closed time-like curves become possible. Paths through space-time that loop back on themselves, that return to the same moment they started from. Near rotating black holes, these curves exist. In certain solutions to Einstein's equations, time travel is mathematically possible. You could, in principle, follow a path through space-time that returns you to your own past. But would this actually work? Or would the universe prevent it somehow? The famous grandfather paradox illustrates the problem. You travel back in time. You prevent your grandfather from meeting your grandmother. Therefore, your parents are never born. Therefore, you're never born. Therefore, you never travel back in time. Therefore, your grandfather does meet your grandmother. Paradox. How does the universe resolve this? There are several possibilities. 1. Time travel is simply impossible. The universe doesn't allow closed time-like curves. Whenever they seem to form, quantum effects or other phenomena prevent them. This is called the chronology protection conjecture, the idea that the laws of physics conspire to prevent time travel paradoxes. 2. The timeline is self-consistent. If you travel back, you can't change the past. You can only do what you already did. Your attempt to prevent your grandparents from meeting fails. Maybe you accidentally introduce them, or maybe you realize you're not actually in your own past, but in a parallel timeline. 3. The many worlds interpretation solves it. When you travel back and change the past, you create a new timeline, a new branch of the multiverse. In this new branch, your grandparents don't meet. In the original branch, they do. Both timelines exist. No paradox. These are all speculative. No one has traveled in time. No one has observed a closed time-like curve. We don't know if time travel is possible or how paradoxes would be resolved. But the speed of light is central to all of this, because if you could travel faster than light, you could travel backward in time. The two are equivalent. Faster than light travel is time travel. This is why the speed of light is an absolute barrier, not just a limit on velocity, a limit on causality, a protection against paradoxes, a fundamental feature of how the universe maintains logical consistency. At light speed, time stops, past and future merge. All moments become simultaneous. This is the boundary, the edge of what's possible. the border between normal causality and paradox. Experimental evidence. Let's talk about evidence. About how we know relativity is true. About the experiments that confirm time dilation is real. The Haffel-Keating experiment in 1971 was one of the most famous. Two physicists, Joseph Haffel and Richard Keating, took atomic clocks on commercial airplanes. They flew around the world, one direction eastward, one direction westward. When they returned and compared the clocks to ones that stayed on the ground, the clocks showed different times. The flying clocks had aged less, by nanoseconds, tiny amounts, but measurable, detectable, real. The eastward travelling clock lost time compared to the ground clock. The westward travelling clock gained time. Both effects matched the predictions of relativity. Both confirmed that time dilation is real. Muons provide another striking example. Muons are subatomic particles created when cosmic rays hit Earth's atmosphere. They're unstable. They decay into other particles with a half-life of about 2 microseconds. Cosmic ray muons are created high in the atmosphere, about 10 kilometers up. They travel toward Earth at speeds very close to the speed of light, about 99.8% of light speed. Here's the puzzle. At that speed, even traveling the speed of light, a muon should only travel about 600 meters before decaying. They're created 10 kilometers up. They should all decay long before reaching the ground, but they don't. Muons reach the surface in large numbers. Detectors on the ground measure them constantly. How is this possible? Time dilation. From the muon's perspective, time is moving slowly. Its 2 microsecond lifespan is dilated, stretched. It lives long enough to reach the ground. From our perspective, the muon lives longer because it's moving fast. From the muon's perspective, the atmosphere is contracted. The 10 kilometers becomes less than a kilometer. Both explanations are valid. Both are different ways of describing the same relativistic effect. GPS satellites, as mentioned earlier, provide daily proof. The system wouldn't work without relativistic corrections. Every navigation app on your phone relies on Einstein being right. Particle accelerators see time dilation constantly. Particles moving at 99.9999% of light speed live much longer than they should. Decay rates slow down. Exactly as predicted by relativity, all of this is evidence. Concrete, measurable, reproducible evidence. Relativity isn't speculation. It's tested, confirmed, verified thousands of times over, and all of it points to the same conclusion. Time is not absolute. Time is relative. Time depends on velocity. Time slows as you approach light speed. And at light speed itself, time stops entirely. The limits of language. We're reaching the limits of what language can express, the limits of what words can convey. Time stopping at light speed isn't really stopping, because stopping implies a process, a change, a before and after. But at light speed, there is no process, no change, no before or after. A photon doesn't experience time stopping. It doesn't experience anything. Experience requires duration, requires moments, requires time. We're trying to describe something that exists outside of time using language built for beings who exist in time. It's like trying to describe color to someone born blind. The concepts don't map. The words don't connect. This is a fundamental limitation. Physics can describe what happens mathematically, can predict outcomes, can explain relationships between measurements, but it can't make you feel what it's like, can't give you intuition for something so far from everyday experience. Even physicists don't really understand it in the way we understand normal things. They understand the mathematics, they know how to calculate, they can make predictions and test them, but the intuitive grasp, the felt sense of what it means, remains elusive. This is okay. This is normal. The universe is under no obligation to match our intuitions, to fit within the limits of human cognition, to be comprehensible in everyday terms. What we can do is push our understanding to its limits, stretch our concepts as far as they'll go, use mathematics when words fail, use analogies and metaphors while acknowledging their limitations. The photon exists in an eternal now. This is the best phrase we have, but even this phrase is inadequate. Because eternal implies time, infinite time, forever, but the photon doesn't experience infinite time. It experiences no time, zero time. Perhaps we should say the photon exists timelessly, but this also misleads, because existing seems to require time. To exist is to persist through moments, but the photon doesn't persist, doesn't endure, doesn't continue. The photon simply is, without qualification, without duration, without process. It is connection, relationship, geometry, and this is as close as words can take us. The beauty of the universe. There's something beautiful about all of this, something elegant and profound. The universe has structure, deep structure, mathematical structure. It's not chaos, not randomness, not arbitrary rules piled on arbitrary rules. It's geometry, symmetry, relationship, patterns that repeat at every scale, principles that unify apparently different. Phenomena, electricity and magnetism turn out to be one thing. Electromagnetism. Space and time turn out to be one thing. Space-time. Mass and energy turn out to be one thing. Related by EMC2, these unifications reveal something about reality, that beneath the surface complexity is fundamental simplicity, that the universe makes sense, has coherence, has beauty. The speed of light is part of this beauty. It's not an arbitrary limit, not a rule imposed from outside. It emerges naturally from the structure of space-time, from the way space and time relate to each other, from the geometry of reality itself. Time stopping at light speed isn't a glitch, isn't a flaw in the universe's design. It's a feature, a natural consequence of how space-time works, a boundary that makes sense, that has to be there for the universe to be consistent. Physicists often talk about the elegance of equations, the beauty of symmetry, the aesthetic appeal of fundamental theories. This isn't poetry, isn't metaphor. It's a real guide to truth. Beautiful theories tend to be true. Elegant mathematics tends to describe reality. When physicists develop a new theory, they look for beauty, for simplicity, for unification. These are signs that they're on the right track. Einstein's field equations are beautiful. 10 coupled nonlinear partial differential equations that describe the curvature of space-time. They're complex, difficult to solve, but they're also elegant, symmetric, perfect in their structure. Maxwell's equations describing electromagnetism are beautiful. 4 equations that unify electricity and magnetism and light, that reveal light as electromagnetic waves, that predict the speed of light from fundamental constants. The standard model of particle physics is beautiful. Despite being complicated, despite having many parameters, it has an underlying symmetry, a gauge symmetry, a mathematical structure that explains why forces exist and how particles interact. And at the heart of all this beauty is the speed of light, the conversion factor between space and time, the boundary of causality, the structure that makes time itself possible. What we still don't know. For all we understand, there's still so much we don't know. We don't know how to unify general relativity with quantum mechanics. These two theories describe reality at different scales. Relativity describes gravity and space-time. Quantum mechanics describes atoms and particles. Both are correct, both make accurate predictions, but they're incompatible mathematically. At the Planck scale, about 1035 meters, quantum effects and gravitational effects become equally important. At this scale, our theories break down, give nonsensical answers, predict infinities. We need a theory of quantum gravity, a theory that describes space-time at the smallest scales. That unifies quantum mechanics with general relativity. That explains what space and time are made of. String theory is one attempt. Loop quantum gravity is another. Other approaches exist, but none are complete. None make testable predictions yet. None have been confirmed by experiment. We don't know if space-time is fundamental or emergent. Is space-time the ground of reality, the base layer, or does it arise from something deeper? From quantum information, from entanglement, from relationships between quantum degrees of freedom? Some theories suggest space-time is emergent, that at the deepest level, space and time don't exist. Only quantum information exists, and space-time emerges as a macroscopic approximation, like temperature emerging from molecular motion. If this is true, then asking what happens at light speed might be asking the wrong question. Light speed might not be fundamental. It might be an emergent property of the underlying quantum structure. We don't know what dark energy is, why the expansion of the universe is accelerating, what this means for the ultimate fate of space-time. Will the universe expand forever? Will it tear apart at some point? Will regions become causally disconnected permanently? We don't know if there are other universes, other regions of space-time with different physical laws, different values of the fundamental constants, different speeds of light. We don't know what consciousness is, how subjective experience arises, whether it's fundamental or emergent, whether it's unique to biological systems or could exist in other substrates. All of these unknowns touch on our question about light speed and time, because they're all connected, all part of the deep structure of reality, all aspects of the same underlying mystery, the personal meaning. Let's bring this back to something personal, something human. What does all this mean for your life, for how you experience time? You exist at subliminal speeds, slow speeds, speeds where time flows normally, where past, present, and future feel distinct, where change is possible and life unfolds moment by moment. This is your reality. This is the domain of human experience, of consciousness, of meaning. Time dilation is real but not noticeable at human speeds. You age at the same rate whether you're sitting still or driving on the highway. The differences are measured in nanoseconds, imperceptible, irrelevant to daily life. But knowing that time is relative changes something, changes how you think about existence, about reality, about the nature of now. There is no universal present moment, no cosmic now shared by everyone. Your now is yours, different from the now of someone moving at a different velocity, different from the now of someone in a different gravitational field. And yet, paradoxically, this makes your present moment more real, not less. Your experience of now is not an illusion. It's a genuine feature of your reference frame, your relationship to space-time, your path through the four-dimensional manifold. You are genuinely experiencing this moment, this unique, unrepeatable, precious moment. It's real, even though someone else's present moment is different. Even though simultaneity is relative, your experience is valid, true. Real time flows for you. Processes unfold. Change happens. This is what it means to have mass, to exist at subliminal speeds, to be made of matter rather than light. Light exists outside this flow, experiences no duration, connects moments without traversing the time between them. This is what it means to be massless, to travel at light speed, to exist as pure relationship. You are not light. You are matter. You are process. You are change unfolding over time. This is not a limitation. It's what makes you possible, what makes consciousness possible, what makes experience possible. Embrace your relationship with time, your movement through it, your existence in it. This is the nature of your being, the structure of your existence. And when you look at light, at sunlight streaming through a window, at starlight traveling across the cosmos, remember that light exists outside of time. It connects you to its source directly, immediately, without duration. The sun you see is 8 minutes old from Earth's perspective, but from the light's perspective, it's simultaneous. The fusion reaction that created the photon and the moment it hits your eye are the same moment. No time between them, no journey, just eternal, timeless connection. The ultimate answer. So let's return one final time to our question. Does time stop when you hit the speed of light? The answer is yes, and the question is impossible, and both are true simultaneously. Yes, time stops, completely. From the perspective of anything traveling at light speed, no time passes. The entire journey, from emission to absorption, is instantaneous. Zero duration. All moments simultaneous, and the question is impossible, because you can't hit the speed of light. Nothing with mass can. The energy required is infinite. The transformation is discontinuous. You can approach arbitrarily close, but never reach it. Light speed is not a speed you achieve. It's a boundary, a horizon, a fundamental feature of space-time structure. The photon doesn't experience time stopping. The photon doesn't experience anything. Experience requires time, requires duration, requires process. The photon has none of these, exists timelessly, is pure connection without journey. This is the deepest answer we can give. Time stops at light speed, and light speed is unreachable, and photons exist in a mode incompatible with experience. And all of this emerges naturally from the geometry of space-time. The universe is telling us something through these equations, through these relationships, through this structure. It's telling us that time is not what we think it is. That reality is deeper and stranger than everyday intuition suggests. That the speed of light is not arbitrary but fundamental. That matter and light are different modes of existence, not just different types of things. We live in a universe where time is woven into space, where past and future exist as real as the present, where motion through space steals motion through time, where light speed is the boundary between time-like and space-like, between process and stasis, between becoming and being. This is not the end of understanding. It's a beginning, an invitation to think deeper, to question further, to explore more carefully what we mean by time, by existence, by reality itself. The equations of physics describe what happens, but they don't tell us what it means. That's the work of philosophy, of contemplation, of careful thought about the implications and significance of what science reveals. Does time stop when you hit the speed of light? Yes, in every meaningful sense. Time stops, completely and absolutely, at the boundary between massive and massless, between time-like and null, between becoming and eternal now. And in understanding this, we understand something profound about the universe we inhabit, about the nature of time itself, about the structure that makes existence possible, the eternal now. When light travels from a distant star to your eye, it's not making a journey. It's not traveling through time. From the photon's perspective, the star and your eye exist at the same point. The emission and absorption are simultaneous. The photon is the bridge, the connection, the relationship itself made physical. This is perhaps the most profound insight relativity offers. That light exists outside of time. That the universe, seen from light's perspective, is collapsed into a single eternal moment. And we, made of matter, made of particles with mass, exist in time. We experience duration. We remember the past. We anticipate the future. We live in the flow that the photon never experiences. This is the gift of mass, the blessing of existing below light speed. We get to experience time, to change, to grow, to become something we weren't, to have a story, a history, a journey. The photon has no story, no journey, no becoming. It simply is, eternally, timelessly, perfectly. Both modes of existence are valid. Both are real. Both are necessary for the universe to be what it is. Matter needs light, needs the massless particles that mediate forces, that carry information, that connect regions of space-time. Without light, matter would be isolated, disconnected, unable to interact, and light needs matter. Needs something to emit it, something to absorb it, something to give it meaning and purpose. Without matter, light would be pure abstraction, pure geometry with no physical manifestation. Together, they create the universe. Matter flowing through time, light existing timelessly, both woven into the fabric of space-time, both essential, both real, the speed of thought. Here's something to consider. Information in your brain travels much slower than light. Nerve impulses move at speeds measured in meters per second, hundreds of times slower than sound, millions of times slower than light. When you have a thought, when you make a decision, when you feel an emotion, electrochemical signals propagate through your neural networks. These signals take time, measurable time, time that you don't consciously perceive, but that shapes your experience. The you that exists in this moment is constructed from signals that originated milliseconds ago in different parts of your brain. Your unified sense of self, your feeling of being a single coherent person experiencing a single present moment, is actually synthesized from many signals arriving at different times. Your brain creates the illusion of simultaneity, makes you feel like everything is happening now. But there are subtle delays, timing differences, propagation lags. In a very real sense, you never experience the present moment. You always experience the recent past, the time it takes for signals to travel from your sensory organs to your brain, the time it takes for your brain to process these signals, the time it takes for conscious awareness to emerge. When you see a star, you see it as it was years ago. When you see the sun, you see it as it was 8 minutes ago. When you see your hand, you see it as it was milliseconds ago. When you experience your own thoughts, you experience them nanoseconds after they occurred. Everything is delay. Everything is lag. Everything is the past masquerading as the present. But this doesn't make your experience less real, less valid, less meaningful. It's just how experience works, how consciousness emerges from physical processes, how matter perceives itself and the universe around it. Light experiences no such delays, no propagation time, no processing duration. It exists at the boundary where signal and arrival are one, where cause and effect merge into a single moment. If consciousness could exist at light speed, it would be very different from human consciousness. Instantaneous, omnipresent along the light ray, knowing emission and absorption simultaneously. No memory because no past, no anticipation because no future, just eternal awareness of all points along the path at once. But this is speculation, fantasy. Consciousness seems to require time, require physical processes unfolding over duration, require the kind of complexity that only emerges in matter with mass. The speed of light is not the speed of thought. Thought is slow, embodied, physical, temporal. And this slowness, this embodiment, this temporality is what makes thought possible in the first place. The poetry of physics. There's poetry in these equations, beauty in these concepts, wonder in these relationships. Time slows as you move faster. Space contracts in your direction of motion. Mass and energy are equivalent. Light speed is absolute. These aren't just facts. They're revelations, glimpses into the deep structure of existence. The universe didn't have to be this way. It could have been simpler. Time could have been absolute. Space could have been independent of time. Light could have traveled at different speeds for different observers. But it's not that way. The universe chose elegance, chose symmetry, chose a structure where space and time are woven together, where matter and energy are unified, where light speed is the fundamental constant that sets the scale for everything else. This suggests something. Not proof, not certainty, but suggestion, hint, intimation. The universe has a nature, a character, a way of being that favors certain patterns, certain structures, certain mathematical relationships. Scientists sometimes talk about the unreasonable effectiveness of mathematics, the strange fact that mathematical structures invented by pure reason, with no reference to physical reality, turn out to describe nature with stunning accuracy. Symmetry groups discovered by mathematicians in the 19th century turn out to describe particle physics in the 20th century. Geometric structures explored as pure abstraction turn out to be the shape of space-time. Abstract equations turn out to predict phenomena never before observed. Why? Why does mathematics work? Why does the universe speak the language of equations? Maybe because the universe is mathematics, is structure, is pattern, is relationship. And what we call physical reality is just mathematics made manifest, made concrete, made experiential. Or maybe mathematics is the language of structure, and structure is what reality fundamentally is. Not matter, not energy, but pattern, organization, relationship. Light, traveling at light speed, experiencing no time, is pure structure, pure relationship, pure mathematics made physical. It connects points in space-time without traversing the interval between them. It is the geometry itself. Matter, traveling below light speed, experiencing time, is structure plus process, pattern plus change, mathematics plus becoming. It moves through space-time, following geodesics, actualizing potential, making choices about which path to follow. Both are real. Both are necessary. Both are aspects of the same underlying reality. The reality that is space-time, that is geometry, that is mathematical structure made experiential, the anthropic shadow. we need to acknowledge something. Our perspective is limited, necessarily limited. We can only observe and understand the universe from our particular vantage point, our particular reference frame, our particular mode of existence. We are matter. We have mass. We experience time. We exist in the subliminal regime where time flows and change happens. This shapes everything we can know, everything we can observe, everything we can understand. We cannot experience light speed, cannot know what it's like, cannot observe the universe from that perspective. We can only infer, calculate, imagine. This is called the anthropic shadow, the blind spot created by the fact that we can only exist in conditions compatible with our existence. We can only observe universe states compatible with observers existing. If time didn't flow, we wouldn't be here to notice. If matter couldn't exist below light speed, we wouldn't exist to ask these questions. If the fundamental constants had different values, stars might not form, or atoms might not be stable, or chemistry might not be rich enough for life. So our observations are biased, selected, filtered through the necessity of our own existence. This doesn't mean our observations are wrong. They're not. They're accurate, true, valid, but they're necessarily incomplete, necessarily limited to the perspective of matter existing in time. There might be aspects of reality we can't observe, can't detect, can't conceptualize, not because they don't exist, but because our existence depends on us being in a particular regime, a particular corner of possibility space. Light speed might look different from a perspective we can't access. Time might have features we can't perceive. Space-time might have structures we can't observe. This is the humility science requires, the acknowledgement of limits, the recognition that our knowledge, however extensive, is necessarily partial, necessarily incomplete, but within these limits, we can still discover truth, still understand deeply, still glimpse the underlying structure of reality. We know time stops at light speed. We know this from mathematics, from experiments, from observations. We know it even though we can't experience it directly, can't observe it from the inside. This is the power of science, the ability to transcend direct experience, to use reason and mathematics to understand regimes we can never visit, scales we can never observe directly, phenomena we can never experience firsthand. The technological future. Let's imagine the future, a future where humanity has advanced technology, where we can achieve speeds close to light speed. What would this mean? Interstellar travel becomes possible. Not easy, not simple, but possible. A spacecraft accelerating to 99% of light speed could reach nearby stars within decades from the traveler's perspective. Though centuries might pass on Earth, time dilation becomes a tool, a way to travel into the future. Astronauts could journey to distant stars and return to find Earth thousands of years older. They'd be time travelers of a sort. Not to the past, but to the future. This creates profound social questions, moral questions, philosophical questions. Should we send people on journeys knowing they'll return to a world completely changed, where everyone they knew is dead, where civilization has evolved beyond recognition? Should we establish colonies knowing the colonists will diverge from Earth's timeline, that communication will be delayed by years, that they'll essentially be independent civilizations by the time the first messages arrive? These are questions humanity will face if we ever achieve relativistic travel, questions with no easy answers, questions that require careful thought about what matters, about what we value, about what we're willing to sacrifice for exploration and knowledge, but will never reach light speed itself, never achieve the timeless existence of the photon, will always remain in the temporal domain, always experience duration, always age, however slowly. Some science fiction imagines workarounds, warp drives that bend space-time, allowing faster-than-light travel without actually moving faster than light locally, wormholes connecting distant regions of space-time, hyperspace dimensions that provide shortcuts. These are speculative. No evidence suggests they're possible. Some theoretical work suggests they might require exotic matter with negative energy density, matter that might not exist, that might violate fundamental principles. The universe might genuinely forbid faster-than-light travel, might make light speed an absolute barrier, not because it's mean, but because causality requires it, Because logical consistency demands it. Because reality needs this boundary to remain coherent. If so, if light speed is truly absolute, then interstellar civilization will be slow, patient, spread over vast timescales. Colonies will be independent, communication delayed, each star system essentially alone. But this isolation isn't necessarily bad. It prevents tyranny, prevents monoculture, allows diversity, allows each civilization to develop its own character, its own solutions, its own understanding, and it preserves mystery, preserves the unknown, ensures that no matter how much we learn, there will always be more to discover, more to explore, more to understand. The ethics of time. If time is relative, if there's no universal now, what does this mean for ethics? For morality? For how we should live? Some philosophers argue that if the future exists as real as the present, then future people are as real as present people. Their suffering matters as much. Their well-being deserves equal consideration. This creates obligations. We should care about the distant future, should make choices that benefit people not yet born, should avoid actions that cause harm centuries from now. Climate change becomes even more urgent from this perspective. We're not just affecting some hypothetical future. We're affecting real people who exist in space-time just as surely as we do. They're just located at different time coordinates. Resource depletion, environmental damage, technological risks, all take on greater moral weight. The people who will suffer the consequences are as real as people suffering now. Distance in time doesn't make them less real, less worthy of consideration. Others argue the opposite. If the future already exists, if everything is determined, if the block universe is real, then what's the point of moral action? Why try to make things better if everything is already fixed? But this confuses determinism with fatalism. Even in a block universe, your choices matter. Your actions have consequences. The future exists, yes, but it exists as shaped by your choices, by your actions, by your decisions. You can't change the future because the future already includes your attempts to change it. Your moral actions are part of what makes the future what it is. Remove your actions and the future would be different. Free will and determinism are compatible. You're free to choose, and your choices are part of the causal structure of space-time. Both are true simultaneously, so ethics remains meaningful. Morality matters. How you live shapes the structure of space-time itself, makes reality better or worse, creates more or less suffering, increases or decreases well-being, and time dilation adds another dimension. If we ever achieve relativistic travel, ethical questions become more complex. How do we balance the interests of travelers and those left behind? How do we handle the fact that moral obligations might be distributed across different reference frames? If a traveler returns after subjective years to find centuries have passed, are they still responsible for obligations they made? Do debts transfer across such vast time differences? How do we maintain social continuity when temporal continuity breaks down? These are practical questions we might face. They require careful ethical thinking informed by relativity, by the understanding that time is not absolute, that moral relationships might span incommensurable reference frames, the creative imperative. There's something energizing about understanding relativity, about grasping that time is relative, that light speed defines the structure of causality, that the universe is stranger and more beautiful than common sense suggests. It expands possibility, opens imagination, suggests that reality is deeper and more mysterious than everyday experience reveals. Artists and writers have long been inspired by relativity. Science fiction explores its implications. Films depict time dilation. Stories play with causality. Visual artists create works inspired by space-time geometry. But the creative response goes deeper than imitation. Understanding relativity changes how you see the world, how you experience time, how you relate to existence itself. When you look at the night sky, knowing that each star's light traveled for years or centuries, that you're seeing the past, that the present moment is relative, that simultaneity depends on reference frame. The sky becomes more mysterious, more profound, more worthy of awe. When you watch the sunrise, knowing that the light left the sun 8 minutes ago, that from the photon's perspective no time passed, that the fusion reaction and your retina are simultaneous in the photon's frame. Sunrise becomes a connection across space-time, a bridge between moments that are one moment from light's perspective. This knowledge doesn't diminish wonder. It enhances it, deepens it, makes the ordinary extraordinary, makes the everyday cosmic, and it invites creativity, invites us to imagine new possibilities, new ways of thinking about time and space and existence, new stories to tell, new art to create, new philosophy to develop. The question of whether time stops at light speed is not just a physics question, it's an invitation to wonder, to imagine, to create, to think differently about reality and our place in it. Every creative work that engages with these ideas adds to our collective understanding, not in the sense of scientific knowledge, though science fiction has occasionally predicted discoveries, but in the sense of cultural meaning, of shared imagination, of collective exploration of possibility. We are meaning-making creatures. We take facts and weave them into stories, take observations and create significance, take mathematics and find beauty. The fact that time stops at light speed becomes more than a technical detail. It becomes a metaphor, a symbol, a door into deeper questions about existence and consciousness, and what it means to be. This is the creative imperative, to take what we learn about reality and transform it into meaning, into art, into story, into shared human understanding. The enduring mystery. We've traveled far in this exploration, from simple questions about time and speed to deep reflections on the nature of reality, from Einstein's equations to mystical experience, from particle physics to ethical obligations, and yet mystery remains, perhaps deeper mystery than when we started. We understand more about time than humans have ever understood. We can calculate time dilation, predict the behavior of clocks at relativistic speeds, design GPS satellites that account for relativity, test predictions to extraordinary precision. But we still don't know what time fundamentally is, why it exists, whether it's emergent or fundamental, whether consciousness creates the flow or merely experiences it, whether the future is fixed or open, whether free will is real or illusory. We know time stops at light speed, but we can't experience this, can't truly understand it from the inside, can only approach it mathematically, conceptually, abstractly. We know space-time is curved by mass, but we don't know what space-time is made of, whether it's fundamental or emergent, continuous or discrete, finite or infinite.